Thanks for joining today's Biogeochemistry Science Friday. Today, Jinyun Tang is going to talk to us about macromolecular rate theory. So take it away, Jinyun.
Okay, yeah. So thanks for giving me this opportunity to talk about something interesting we've been working on recently. So the title is, I try to be provocative, like say we always talk about like we want to get the right answer for the right reasons. But then recently, when we look at the literature, for example, this temperature sensitivity of biogeochemical rates, and we found actually there is a recent popular theory called macromolecular rate theory is doing the right thing for wrong reasons. So, and before that, actually, I will start with a small quiz. We always say like, people say like all models are wrong, but some are useful. And do anybody know who's the first to say it? I give you 1 minute.
Aristotle?
Nope.
Some guy named Box, right?
Yes, you're a genius, Forrest. Yeah. Okay. So yes, it's the statistician. The George Box said that, and you know, when I look at actually you can find about in his biography. So when people interview him, they always quote these words. But actually, when he said that, right in the paper, in this very interesting paper he wrote in 1976 about science and the statistics. So actually, he did not directly say the full words, like say, essentially all models are wrong, but some are useful. But he said in two different ways. The first one is about parsimony. So he says like, since all models are wrong and scientists cannot obtain a correct one by excessive elaboration. And the second one is like, okay, so when you talk about model, we should worry selectively. He says like, the scientist must be alert to what is important to run. It's really hard to guess what he really means by the time, but like after reading the paper, the message I get from there is, when a model is wrong, it cannot be corrected by continuously or elaborate or like deliberately benchmarking with more data. And the second one is like, when you feel the model is wrong, and perhaps it's very important to check its foundations. And that's the idea we take to the work we're going to talk today. So like I mentioned, so there is a macromolecular theory. It's about how biogeochemical rates are going to respond to the different temperature. So this is I think it's a first order question for us care about biogeochemistry, climate feedback, or in general biogeochemistry. So, and it's also being taken care with a lot of effort historically. So for example, on the left here, here I show the temperature response or temperature sensitivity curve that's been adopted by the Century model to simulate such as the heterotrophic respiration and the nitrification and denitrification, all bunch of stuff. So in the early days, it's recognized that actually the biochemical rates first increase with temperature and then drop off at high temperature. But then when we look up into literature, it seems like, in the Serrado paper, which they reviewed all the temperature sensitivity curves people use in all the biogeochemical models, pretty much like that's been joined in the past IPCC reports or like CMIP studies. So you can see like there's all kinds of temperature sensitivity curves being adopted. So, and then questions like, okay, which one is right? So, and then also by the time about like 2013 or 2014-ish, some people propose like, yeah, it's not reasonable to expect that the respiration will increase continuously with the temperature, because at some point organisms are going to be dead, or actually they are dying. So such the respiration going down before combustion comes in and further ramp up the CO2 or like other gas emissions. So they argue the macromolecular rate theory is way better than all these different curves to describe how biochemical rates going to respond to temperature. So they demonstrate a number of studies support this statement. So for example, on the left here is a paper done by Elster et al. They synthesized many incubation experiment, which measure the biochemical rates such as soil respiration or nitrification rate. I think some even include like denitrification rate. They were able to fit the MMRT, like some MMRT curve or the function to their data very reasonably. And in the middle is another guy. So another group of people, they applied the same MMRT function to leaf respiration because they were saying, yeah, since MMRT is describing the biochemical rates and biologically speaking, plants and the microbes, they're not much different. So they will also again find the MMRT can able to fit the respiration or the tropical respiration versus temperature curve very well. And it's much better actually than the Arrhenius curve. And also some empirical curve you will find in the literature. And more recently, so if you look up Google and very quickly you will find there's a study about applied MMRT to describe the human neural membrane conductance to cations such as sodium or potassium, etc. So they measured all kinds of rates for different cations, and they're able to fit the MMRT curve really well. So it's fair to say MMRT is empirically possesses supremacy compared to the Q10 or traditional Arrhenius curve. And beyond that, and even to some extent, as the author have done, we can even claim MMRT has the theoretical supremacy as well. So which can be appreciated by looking at the equation. For example, here's the equation of the full MMRT. What it says is the biochemical rates is a function of temperature with all the parameters such as the Boltzmann parameters and the Planck parameter and the Gibbs free energy, where the Gibbs free energy can be write into explicit form as a function of enthalpy and heat capacity, reference temperature, and the entropy as well. So it's all looks beautiful, and meanwhile can explain the data really well. So especially it can describe these kind of behavior of enzyme catalyzed biochemical rates. Now it's like, now the question is like say, as someone have working on this problem for quite a number of years, so I actually have some uncomfortable feeling about it. So then we decide to okay, so then there might be something wrong. So the next thing is, okay, so the first thing I look at it is like even we know like heat capacity can be negative, but then we look at that. So we look at it enzymes. The MRT predicts that there's a deterministic relationship between the heat capacity of the chemical reactions versus the optimal temperature, where the optimal temperature is something defined here, where the biochemical rates peaks. So it implies it gives some very strong implications, such as like enzymes, biochemical reactions as a fixed optimal temperature. And then if we're able to measure this heat capacity, then we're able to quantify like how microbes adapted to new environment, such as warming or some other things. So with all this, and okay, so like I mentioned, I feel my experience make me feel question the validity of the MMRT. So we decide like to look it up, the original paper, how their theory being developed. So actually we found something questionable, especially about their foundations. So but to tell why how we come up with the idea and why they are wrong, I would like to do present the analysis in the historical context. So I will start with a review of other literature. So this is the curve we found like in the paper published in the 1930s, and people analyzed the microbial growth rate. I think about it, there was E. coli. So microbial growth rate as a function of the temperature, they were able to derive this kind of curve. So which fit there's some empirical regression really well. And meanwhile, by looking at this paper, so here there's a paper about temperature and the book about temperature and life, which is freely available from Springer. You can download it from online. They documented many previous studies about how biological growth rate or biochemical rates varies with temperature, and there they documented that like people know that the growth rate increases with temperature and decreases with temperature in as early as like 19th century or like, and then and also they developed so-called degree day model, which you will find perhaps in for plant physiology in some literature. So it's well known that this biochemical rates is a non-monotonic function of temperature, and by 1946, the Johnson and Lewin they studied E. coli, and actually they were able to develop some theoretical explanation why the biochemical rates would have increased with temperature and then drop off that. So the idea they get there is okay, so for the E. coli they were studying, they were saying the growth of E. coli is bottlenecked by some control enzymes. So but the control enzymes, because it's a protein, and by the time when I think people study the protein physics, they know the protein would deactivate it, partially deactivated due to conformation, or like due to thermal motions. So they apply that idea into a theory. They were saying, okay, so there's a transition between active and versus inactive states, and which they were able to derive a overall growth rate as a function of this is the transition state theory. So from Iring's the Iring's transition state theory, and then also this denominator accounts for the fraction of enzymes are actually active. So they were able to fit the measurements with their equations quite decently. So, but after many years, about 30 years after that, and there's another very classic work done by Peter Sheppy and Don DeMaco, and they extended their assumption about their theory about the transition between active enzyme versus inactive enzyme. What they were saying is, yes, the growth of the organism they were analyzing is bottlenecked by some control enzyme, but then the enzymes actually exist in 3 states rather than 2 states. They were saying because at any given temperature, because the temperature is fluctuating and would drive some the enzymes to the cold activated, and then part of the enzyme become heat inactivated, and the 3 states they achieve some kind of equilibrium. So they formulated the idea, used the statistical mechanics, and applied Iring's transition state theory to all the coefficients, and then assuming steady state, they were able to derive. So this is the probability or the fraction of the enzyme at a given temperature could be catalytically active. So then they apply this together with the mechanism-maintained kinetics. So it's many of us know from our learning of the photosynthesis process. For example, like say there is substrate plus enzyme and goes through complex and produce a product. So they applied this, the fraction of active enzyme combined with the mechanism-maintained kinetics. They were able to they assume because it's really hard to measure the substrate. They're simply assuming like, yeah, maybe so the organism they're studying are not substrate limited, so they derive these biochemical rates as a function of temperature with a whole bunch of parameters that's some of empirically derivable and some are universal constant, such as the Boltzmann constant and the Planck constant. So, and so one thing I mentioned, like the key assumption about the Sharpe and the Macro theory is enzymes are undergoing thermally reversible denaturation. It could be go towards the cold deactivated or like heat deactivated states. So they based on their they propose their assumption based on a lot of measurements. So here, okay, sorry, this paper should be like 1973. So there are a lot of studies indicate enzymes or proteins in general undergoing these kind of thermal denaturation. And they even can, enzymes can even do that in the absence of substrate. So, and then with the good assumptions and built into their theory, they tested their model with a bunch of organisms from E. coli and some other bacteria, and even fruit flies. So they were able to demonstrate that their theory, their equations can fit the measured temperature dependence of growth rate really well. And also comparing to the Array model, which basically describes the abiotic chemical rates or chemical reaction rates. So their theory is able to account for the biological fall off of chemical rates at high temperature rates. So it's all going well. So let's recap the Sharpe de Macro theory before we dive into our analysis with and the proposal of new theory. So there are basically three concepts. The first one is there's active states. Not all enzymes are always not all enzymes at the temperature are in active states. And the other things is the biochemical rates can be described by the mechanism mental kinetics and as a function of substrate and also the enzyme balance, of course. But they propose like, okay, so in the denominator, because the enzymes exist in three states: cold, heat, deactivated, and active states. So they have this quite complicated equation to account for the fraction of active enzyme. So meanwhile, there's a lot of have been going on in the community who study protein physics, and particularly they were able to come up. They were able to demonstrate that the Boltzmann law from thermodynamics can describe the transition between native enzymes, which are called like active enzyme versus a thermally inactive enzyme with a single, much easier, the Boltzmann function. So and this basically describes is the unfolded states, or like the inactive states, it's a function of the active states, and also once across this energy barrier denoted by this Gibbs free energy, and we can calculate the fraction of enzymes at any temperature that are being active. And also the other thing to mention is that because their theory is based on Gibbs free energy, and we from the chemistry thermodynamics we know we can derive functions, the change of Gibbs free energy to change of temperature, pressure, and even electromagnetic field, and also salinity, all these kind of things. So which points to like, if we adopt to this more general at least more general theory, so we are able to describe the temperature dependence of enzyme catalyze the chemical rates for more broad environmental changes. So so we adopt this idea, and again, so we say we adopt the Boltzmann-based calculation of active enzyme fractions, and combined with the Maclaurin-Menten kinetics, obtain so-called chemical kinetics theory. So from there, we're able to derive the chemical rates can be computed from this equation, where we have this maximum catalysis rate, which is Vmax, we often call it, and also the fraction of active enzyme, and also the substrate function, substrate availability, and the half saturation constant. And more importantly, because we based our formulation all on thermodynamics, we're able to derive the temperature dependence of Vmax explicitly, for which we can see is the transition state theory, and also we can derive the temperature dependence of K. So which we found, interestingly, it's just the Arrhenius temperature type of dependence. Based on this, and then we come up with this equation of chemical rates as explicit function of temperature, and there we see we have three types of temperature dependence. The first one is describe the transition state theory, and second one is describes the partition between the active versus inactive enzymes, and finally there was the K, the half saturation constant. Its temperature dependence is described as a Arrhenius type of function. So we can link this with the macromolecular rate theory. Well, in their study, they were saying attribute the whole chemical reaction rates to these simple equations without taking account of the substrate dependence or the temperature dependence of these half saturation constant. So what they are effectively doing, we can demonstrate by these equations. So the MMRT theory is describing these biochemical rates actually involves a whole bunch of stuff. So including substrate abundance and the three types of temperature dependencies. And the other thing, more importantly, is when we read their paper very carefully, we found that why they come up with this assumption is they did their study. Just to mention, like the MMRT is proposed based on enzyme assays, and then later on being generalized to a whole bunch of studies, such as like a whole bunch of studies based on the control enzyme hypothesis. But then when they were trying to derive the equation, they made a very strong assumption is in their enzyme assays. They were saying they are adopting a substrate concentration high enough at they are reference temperature such that they are measured biochemical rates have no substrate dependence, temperature response have no substrate availability dependence or difference on the behavior of K versus temperature, which of course, as we found, is not quite true. So, and to demonstrate that our chemical kinetic theory can reasonably reproduce what they did, so we then applied our equation to all the data they used to demonstrate the MRT theory is great. So here we found is our chemical kinetic theory are equally great. At least it fits all their data almost perfectly. With R squared is some of them even close to 1.00. So, but besides that, we found something very interesting. So remember that the MMRT predicts for each biochemical reactions, there's unique optimal temperature, which they were saying that could be characterized as enzyme traits, or like for organisms could be like organism traits, or for example, come to microbe, and microbe traits come to plants, and maybe the plant traits. What we found is not quite true, because because by the chemical kinetic theory, we're able to resolve the substrate availability dependence. What we see is as the substrate level increases, actually we have this optimal temperature shifting towards higher temperature, which means if we're considering the shift of the temperature of a kind of evolution adaptation, that's not necessary. It could be just a short-term acclimation due to the change of substrate or something else, something alike. So and then okay, so with that, what I'll criticize is that okay, so the MMRT theory, they did that based on the transition state theory and demonstrated with the equation that a very good performance of equation and with very elegant meanings of all those parameters. But then the question is, besides what our criticism, so what else is going wrong with their theory? So one thing I remind you is one key hypothesis in this equation is the heat capacity of the biochemical rates, the temperature dependence of biochemical rates is non-zero. And then some people recently did a molecular dynamics simulation for the enzymes they explored. So or like the enzymes they studied using the MMR in the original MMRT paper. So what they found with quantum mechanics, they found is the CP, the heat capacity, which claimed to be non-zero in the macromolecular rate theory, is actually zero. So this is demonstrated by a linear function or a linear dependence of the overall Gibbs free energy as a function of temperature. So here's the overall Gibbs free energy. We see it's linear, so this heat capacity should be zero. And the second one is they also analyze the component-wise of those involved in the enzyme catalyzed reactions. For example, the transition state, or like the reactant state, which say describes the binding between the enzyme substrate, and they calculate that overall energy. Actually, they also found a linear dependence with temperature. So which another indicator says the heat capacity is zero. And they also calculated the Gibbs free energy for the transition state. Again, they found the heat capacity should be zero. So therefore, combine our analysis of the original assumptions and also the molecular dynamics simulations, we're saying the seemingly very elegant macromolecular theory is actually not right. So it's for in terms accounting for observations, for example, it cannot, or it ignores the existence of reversible temperature-driven, thermally driven enzyme denaturation, and also it introduces a negative heat capacity which does not agree with the chemical reaction theory that's based on quantum mechanics. And also, if we look at original analysis, we found the original parametric fitting make a very strong assumption is the substrate dependence. There's no substrate dependence, and also the half saturation constant is temperature independent. Both of these are not quite true. So and finally, it makes a somehow misleading prediction, such that like the optimal temperature is a biological trait. What we show here is it's not. It's a sort of like dynamic emergent consequence, combines the biological traits and also the substrate availability. So overall, we can only say is while MMRT is being very successful, it's just another empirical approximation that's perhaps better than Q10 and the popular Arrhenius curve. So and its mechanistic its mechanistic advantage that is not supported about our mechanistic analysis. So, and when it comes to, okay, so we start, there's a lot of implications. For example, I can mention multiple times, optimal temperature is not biochemical rate traits. So, which I think many models, many biochemical models of microbes and also plants trying to take this as a fixed parameter or a trait parameter, which we have say it's probably not quite true. And the second one is with warming, and the organism can adapt to or climb to warming by shifting substrates or change of substrate availability due to the change of substrate availability. So it's could be some kind of either like active or passive process. And finally, perhaps if we are able to apply this our chemical connective theory to the photosynthesis scheme in current models, maybe we will get some new insights about the CO2 fertilization effect combined with warming. So then finally, the question is, how can we better characterize the temperature dependence of biochemical rates, which is still the first order question we needed to address in our modeling of biochemistry. So the suggestions we have is like for enzyme assays. So perhaps when people doing this measurement, people should measure the temperature response at a multiple substrate levels rather than assuming give a lot of substrate, like say always going well. So that's may not work. And the second one is for general reaction rates, and we just need to measure the substrate availability together with the temperature response. Organisms perhaps is use the more comprehensive, complete theory to synthesize as much data as possible. And finally, our study indicates like we also with this some previous study in the literature on microbial biochemistry is perhaps proteomic data can help us constrain the biochemical rates if we combine the statistics with the chemical kinetic theory. So aside from that, I think we also learned something philosophically. So the key things I think I like to remind myself is that when empirical data is insufficient to reveal a model's problem, maybe it's very important to reanalyze the theoretical foundation of the models. So which I unfortunately, we usually don't see a lot in the current literature. So, and the second one is perhaps we should advocate or like actually use more first principles in formulating our model equations, because from all the knowledge we know so far, the first principles are quite consistent, which means first principles are those basic equations we learn about energy, mass, and transfer, or like then the thermodynamics. So those by putting those together, perhaps we were able to come up equations that's mechanistically more sound, and perhaps it's can be making predictions that cannot be revealed by existing measurements. So, and that's all my talk. Yeah, I'm ready to take questions.